Hello, and welcome to this tutorial on exponents, which is the math behind compound interest, a very important concept in finance. So let's start by looking at what the exponential expression is, v to the n, where v is the base and n is the exponent or power. For example, if we're looking at Vn and n is a positive integer, it just means that we're multiplying v by itself n times. So for example, if we had 5 to the third power, that just means 5 times 5 times 5. So there's 5 by itself 3 times, and that would equal 125. Now in finance, exponential expressions are used to express compounding rates of return. So in this case, the base is 1 plus r, and r here is the rate of return per period, and n would be then the number of periods that we're compounding. So for example, if we have $100 that's invested at 10% per annum, PA stands for per annum, for 3 years, the investment grows to this amount, 133.10. And how do we get that? Well, we have $100 times 1.1, where 1.1 is 1 plus 10%, and we take that to the third power. And on our calculator, it would be like this. So after clearing, we would enter 100 times 1.1, hit the YX key to bring it to the third power, hit 3, hit equals, and you will see 133.1. So you should be able to replicate that on your calculator. Now, exponential versus linear growth is an important concept, and let's see what that means. Well, linear growth essentially means we're not getting this compounding. So if we think of that, a finance example, if we had $1,000 and we were earning 6% on the 1,000, but we weren't earning interest on the interest, so we were just getting that 6%, same 6% on the 1,000 every year and accumulating that, by the end of 30 years, we would have $2,800 in our account. So it would essentially be linear growth. It would grow in a straight line like this. Now, if we had exponential growth, we're getting the compounding. So basically, that means we're getting the interest on previously earned interest. So the formula would be here. And so using the same 6% growth on $1,000, we take 1,000 times 1 plus 6% to the 30th power, and we get a much larger number, about twice as big. So that would be approximately 5,743.49 rounded to cents. And if we looked at that graphically, much divergence. And you see in the beginning, it doesn't show much difference, but as that compounding interest starts to pick up, the difference gets quite large. Now, this is, of course, where the interest rate is positive, which is normally what you would expect, and you're getting a positive return over long periods of time. But there are situations where you might actually have negative returns or negative a loss somehow, and where in that case, let's just say we had negative 6% for 30 years. So we'd use essentially the same formula, but instead of plus 0.06, we'd use minus 0.06. And we take that to the 30th power, and we get a number much less than 1,000, 156.26. And if we graph it, it will go to here. Now notice that rather than accelerating, we're kind of decelerating, and it will never go below 0. It will never go below 0 because you're basically losing a percentage of the remaining balance, but it will approach it over time. Okay. Now, let's look at an example involving compounding frequency. This is a common finance application. So the question is, what rate per annum compounded annually is equivalent to 12% per annum compounded quarterly? Now, the key thing to answering these types of questions is first to understand correctly what it means, and in particular, what 12% per annum compounded quarterly means. Well, what it means is the 12% is divided by 4 quarters in a year, and it means we're getting 3% paid quarterly. And so that's what's compounding. We're actually getting the compounding on a quarterly basis instead of on an annual basis. And it's asking what is the effective interest rate we get at the end of the year. So we'll since we're getting interest on interest, we should expect to get more than 12%. So how does that work? Well, let's assume we have $1 invested at 3% per quarter. So after 1 quarter, we have $1 times 1.03. And then after second quarter, we get 1 times 1.03 again on that balance. So we have 1.03 squared at that point. And we get another 1.03. So we're up to 1.03 cubed. And in the fourth quarter, we multiply by 1.03 again, and we get $1 times 1.03 to the fourth. So the interest for the year then is that amount, which we'll show in a second, less the $1 of original principal. So this is the calculation, 1.03 yx to take it to the fourth power, representing the 4 quarters, subtract 1, which is our principal, equals, and we get 0.1255 and some more decimal places. So if we multiply by 100 to see what that is in percent terms, it's going to be approximately 12.55% or more. So what that means is that this 12% compounded quarterly is equivalent to getting 12.55% if it was compounded annually. So you got all the interest at the end of the year rather than intermediate interest. So let's, why don't you try to do this problem using what we've just discussed. So we have $100, it's invested at 10% per annum, compounded semi-annually. And the question is, what will be the investment value? So we're not looking for an equivalent return, but it's value, total value after 5 years. So there are 4 possible choices here. Why don't you pause the video and see if you can get the correct answer. Okay, so this is the solution. The key here is to recognize what 10% per annum compounded semi-annually means. It means that you're getting 5%, 10% divided by 2 every half year, every 6 months. And further, there are going to be 10 periods because 5 years has 10 6-month periods in it. So you take the 5 times 2. So we would apply the same formula, but with those adjustments. So it'd be $100, which is our initial investment, times 1.05, that's 1 plus our 6 months interest. And we're going to compound that over 10 periods. And that will be rounded to the nearest cent, 162.89. And this is how you would do it on your calculator. So if you got 162.89, congratulations. So let's summarize this tutorial on exponents. So first, exponents, exponential expressions are a compact way of reflecting a serial multiplication. Exponents are used in finance, very importantly, to reflect the compounding of interest over multiple periods of time, years into the future, for example. Exponential growth explodes over time, reflecting this compounding effect and way exceeding linear or uncompounded growth. And when the growth rate is negative, this becomes exponential decay, with the results approaching 0 over time. So if you need more review of the sort of introduction to exponents and particularly exponential growth and decay, I will refer you to this link in Khan Academy on growth and decay. And here I'd recommend only going in on the material up to and including quiz 2. So you might, again, try the quizzes, see how you do. The quizzes have hints. There can be videos about particular problems. There can be practice problems that you can try. So do that if you need to. Thank you for listening.